Okay, great. And can I please ask you to put your, let me just do this. Yeah, and just make sure your microphone is mute, please, so I just don't get distracted. Thank you. Okay, so now that we have learned some fundamental bits about Python, obviously there is far more to learn, in terms of Python coding and the libraries that we covered so far, like pandas and Seaborn or Matplotlib. Uh, there is far more to learn, but it has given us necessary foundation now to start touching on, um, implementing some machine learning, basically, using our existing skills. And that's what we are going to do. But what is far more important prior to us touching on machine learning is certain aspects of it. Let me make an analogy. Imagine you want to start driving a car, okay? When you want to start driving a car, part of it is for you to become competent in terms of using the steering wheel, the gear, the gas, the clutch, brakes, or the know-hows of how to operate a car. Okay, so that's one thing. But at the same time, there are rules and regulations. Yeah, so you can be a good driver in terms of sitting behind the car and like pushing the gas. But then there are these rules, okay, what do you do when you get around the roundabout or when you see a traffic light or where there is a pedestrian walking across? It's very important that you, of course, understand all of that, as well. So before we touch into the techniques of machine learning, there are few concepts that I really, really want you guys to first become familiar with, and understand. Obviously, for our sessions, we don't go too much in depth of, knowledge, but I want you to have a foundation on it and understand the concept. Yeah. So as such, I will be basically touching on these points first, and then we carry on into actually, okay, how do we do it in Python? So machine learning introduction. Um, what is machine learning, guys? So you see, like some people would make the mistake, especially engineers or people who do physics, yeah, that okay, is machine learning something like simulation? Well, no, it's not. Is it similar to a statistical analysis? No. Okay. What is the difference? So I've written here the ultimate goal of machine learning is making predictions, okay, and not so much interpretation of the data, okay? So compared to inferential statistics, for example, where you try to look into a data and explore what is embedded, what is the relationship in there. So, for example, you would get like for example, econometricians, people who study economics at mathematical and statistical level, they are very much interested into understanding, okay, this data, what does it tell me? Why two parameters have a certain relationship? So that's inferential math or statistics or whatever, yeah? Whereas machine learning ultimately is not dealing with that. It's all about you giving your model a set of data and for the model to be able to predict the outcomes for you. But it would only do so as well, provided that you have trained it with enough input data and relevant predictions associated with those data. Okay? So it's very important to understand that. Yeah. So machine learning algorithms are basically able to learn in a sense, if you want to use that term, yeah? So they are able to learn from the data that you train them with, and they can, like the more complex models you use, they are able to learn complex patterns, okay? And they can learn also in high dimensional data, okay? So for example, high dimensional data means how many inputs you actually like have into your model, and what you're trying to predict. Is it just one input and one output, or is it multiple inputs and a single output and such, okay? So obviously they work in high dimensional data as well. Now, at its core, machine learning, when you want to construct a machine learning model, you construct a model and you need to define some evaluation metrics for it, okay? So let's say we just made a really great model. All right, cool. Well, how do you know if your model is good? Obviously, you would check its performance, okay? What performance with what? Performance in terms of when you give it unseen data, is it able to efficiently make correct predictions or classifications or calculations, okay? So you have to use certain evaluation metrics to assess that. And a very, very, very important aspect when it comes to machine learning is the idea of bias and variance, yeah? And it's so important that you understand that. Whether you do deep learning or machine learning, the concepts of bias and variance, and they usually refer to it as bias variance trade-off, is highly important for you to learn. I'm not going to so much focus on resampling learning and learners, ignore that, but I rather you have these three first fundamental concepts that you need to be familiar with when you want to do machine learning, and we will touch on them sort of, yeah. Here I have a mathematical relationship, y equals function of x and a theta, okay, plus some epsilon. Now, usually you see y equals function of x, yeah? I mean, that's what we are mathematically, or at least in algebra or calculus, basically, we have become familiar with. But if you conceptually think of it in a machine learning sense, well, you can refer to it in lingo, like machine learning lingo. Why you can refer to it as response, dependent variable, output, or you can call it the target. Yeah. So whenever you hear any of these terms, you're referring to that y, basically, something that you want to predict or classify or estimate. Then you have your X, which is some may call it predictors, independent variables, the input, or features, okay? So you see target and features are associated with machine learning lingo, okay? While maybe statisticians or physicists or engineers use other terms, basically. Okay. And then you got theta, the estimates, the specifications or parameters, okay? These really refer to the parameters of your model, okay? So gradually when we move forward and I tell you about, okay, we got certain models when we have hyperparameters and parameters, yeah, that would start making sense what we are referring to. But ultimately, this is what typically, if you want to illustrate a machine learning model, that's what you can do technically, like try to define it as such. Okay, now let's look at the most important factor in machine learning, which I said is the bias variance trade-off. Okay, now imagine you want to look at a relationship between the height and weight of people, male or female, doesn't matter. Okay, so if let's say you go and collect the data of thousands of people and you get their height and you get their weight, and you plot them against each other on a two-dimensional axis, basically, or a canvas. Let's say you get some relationship like that. All right. So the idea is, let's say we want to make a machine learning model that, I mean, this is really over super simplified, but I want you to grasp the idea. So can we like make a model that once we give the weight of the person, it can go and measure its, like calculate or predict its height, let's say, yeah, hypothetically. Um, that's the idea. For example, let's say we want to create a best fit line that is capable to take in weights as inputs, okay, remember, or as features, yeah, as a feature, and measure a target, which is going to be your height, yeah. So, I mean, that's the idea, to make a fit line that would basically assist us in doing that. Now, if we think about it, I mean, how many lines can you draw, guys? Just think about it, yeah? You can draw numerous lines and claim for it to be the defining the relationship between these two factors, weight and height, okay? But what is the best way of doing it? So I've written bias. The inability of a straight line to capture the true relationship is bias. Let's ignore this, okay? Maybe if we can go and simplify it. Let's say somebody comes in and says, do you know what? I'm going to define the relationship between these two by getting my pen and literally connecting every single point I see here and say that, okay, this is my sophisticated fitted line. So if you give me a weight, I can just go up there, touch on this red line, and I can predict the height, basically. And that's my model. Or alternatively, somebody might be going like with a straight line, saying, no, I'm going to define a best fit line, a straight line, and just as the other person claimed, I'm going to be able to sort of make an estimation of the height when you give me the weight and, like perform that prediction as such, right? Now, there is some problem, or you can assume there is some problem with both of these models. So let's say we have created two machine learning models that went and created these two lines. So our model one went like that, and the second one went and created this highly, basically, elaborated line, that defines the relationship between these points. Then that's where the idea of bias and variance basically becomes more apparent, yeah? These terms like variation refers to variations in fits between these tests, especially if you are new to it. I want you to just ignore it, yeah? So let's have a better definition of it. Now, take a look at that, yeah? High bias. We would say this model, which is oversimplified, is high bias. This model has a high bias and it has a low variance because it's oversimplified. Okay? It's oversimplified. And this model, low bias and high variance. Yeah? So now it's the other way around. We have increased the variance while we have minimized the bias. Okay? Shall I use the example that I used a couple of weeks back for some of my students? Imagine you got 10 guests, yeah? So 10 people, 10 of your friends are coming to your house, and you want to order a pizza for them, all right? Let's look at this idea of bias and variance in that context. So you want to order a pizza for the dinner, and you got, I don't know, 20 guests, yeah? One way to do it is that you pick up the phone and you call Domino's or whoever is your favorite and you say, hello, can I have 20 chicken pizzas? Let's say chicken supreme or whatever they call them. Okay, so right away, 20 chicken supreme pizzas. That's one option. So the guy comes in, gives you the 20 pizzas, you bring it to the people. Now, there are some who love the chicken supreme, there are some who might be vegetarian, there are some who might hate chicken, there are some who love pepperoni and they just associate pizza with pepperoni, but that's the case. You oversimplified the situation. So your approach to ordering pizza was very biased. It basically was so simple that you went for one option, you ended up satisfying a few people, and majority were not that satisfied. So when they leave your party, they're probably going to say, oh, you just ordered some rubbish pizza. The other way, the other approach is that you say, you know what? I'm going to look into the menu of Domino's Pizza and I'm going to order every single pizza that is there. So when it comes in, everybody's going to be, basically very satisfied. So you have introduced a variation in a sense. So you suddenly have a very high variance but you have a very low bias. Okay, so which approach is right? Well, in the second approach, you would be wasting a lot of pizza and a lot of money. Okay, and really, it was not necessary, for example, for you to order anchovies with, I don't know, oysters, pizza, or like something crazy that happens to be in the menu specific for some people. Now, the idea of creating a balance between variance and bias is so fundamental in machine learning models, okay? So it's very important that you ensure that the model that you design, you create a balance between your bias and variance. So how do you do that? Well, that goes by the way you choose the parameters to structure and train your model, okay? In the case of the pizza example, it was just you making a decision on, okay, hello, Domino's, what pizza I order. The same similar thing applies in a machine learning model, and that's what parameters do you use in constructing your model? It lets you create a balance between bias and variance, yeah? So ultimately, you want like nicely balanced bias and variance factors when you design a model. Okay, let's just ignore these. And then there is this idea of overfitting that we would be using. You see here in the picture, you got two guys and they're wearing suits, yeah? Now, the guy on the left has a suit which obviously is too big for him, and the guy on the right is probably just suffocating in that suit, all right? Now, what is this about? Why are we using overfitting? Because you will hear this a lot and you need to become super familiar with the idea of overfitting. Imagine when you go to if you're a girl or a boy, I don't know, like you go to some tailor and you say, I want you to make me this dress or this suit or something. And you say that, can you make it, to fit me perfectly? And this tailor, being super obsessive, literally uses some sophisticated measurement tapes and measures your body such that the dress he makes you or the suit that he makes you fits your body as if it's a skin on your sitting on your body. Okay? Well, so long as that dress is going to be worn by you on that moment, on that day, where you are at the tailor, well, happy doopy, it's really good. It's perfectly fitting your body. But if you gain or lose weight slightly, or if you try to give this dress to somebody else, it just won't work, okay? It only fits you in that moment, okay? That is the term overfitting at its concept, okay? Now, all right, a person, a suit, so how do we go with machine learning data? All right, think of yourself as the data. Think of yourself as the data, and think of the suit as the machine learning model, right? If a machine learning model is designed such that it performs fantastically with a set of training data, just like as the suit or the dress was fitting only on you, it's overfitting you. It's overfitting the training data. Which means if you throw some test data at it, it's going to be complete rubbish. All right? And that's what overfitting refers to. It means when you make a machine learning model and this model is basically no good. Well, no good in terms of it's only suitable for the training data that it was trained on. Otherwise, if you give it unseen data, which is the objective of machine learning, it would produce garbage results. Okay? Now, what I like to bring to your attention, let me take this away. So what are we going to do in this course in the coming weeks, basically, until end of March? Yeah. So let's look at this picture. As you can see here, I have classified structured what we're going to be learning. So machine learning. The machine learning itself is divided into supervised and unsupervised machine learning techniques, some of which we are going to be touching on. Obviously, there are more techniques here, but we need to think of the scope and how much time basically we have, and also which ones I'm comfortable, teaching you properly. So we are going to be looking at supervised, so supervised machine learning models, okay? And we are going to first cover all of them. Now, when you say supervised machine learning models, they can be either regression, which means you deal with numerical data or numerical output, or it can be classifications, okay? For example, a typical regression, when you want to come up with a real number at the end, you want your model to predict a particular number, that's a regression. Whereas if you want to classify, for example, you are giving the results of a blood test to a machine learning model, and it's going to predict if the person has, I don't know, corona infection or not. It's like yes or no. That's a classification problem, okay? So we will look at both regression models and classifications, okay? But they are separate completely. The way they operate and everything is totally different. So we will look into them. And once we cover these and you become, so we start with basic linear regression model, which I will cover today. Then if we will look into polynomial regression, k-nearest neighbor regression, support vector regression, and random forest regression. Then we will look into logistic regression, this is a classification, k-nearest neighbor classification technique, support vector classification, and random forest. I would then introduce you to the idea of unsupervised learning, two techniques. One is clustering, where you have unlabeled data that, well, I wouldn't discuss it so much now, but when you have unlabeled scattered data and you want to cluster them into groups, basically, but using machine learning, right? So we will cover that, and dimensionality reduction techniques. But with that, we go with k-mean clustering. That's another unsupervised machine learning model. And dimensionality reduction via principal component analysis and LDA, all right? And once we've done this, then we start going toward deep learning. Now with deep learning, of course, just like machine learning models, they can be used for regression or for classification, okay? And specifically classification, we will dive into computer vision as well, all right, in the coming weeks. So literally everything we do through machine learning models, we will also touch on when we go into deep learning models. So by the end of this course, I'm hoping that you will ultimately have learned the necessary amount of Python that we have covered, and implementing your Python skills and your knowledge into analyzing data using the techniques observed here. Now, one thing, if I find time, I will also try to cover these two, yeah? Now, these are not really machine learning concepts inherently, like support SVD and time series analysis, but they are so cool and they're so important. I mean, especially time series, people are beginning to use, like deep learning techniques for time series analysis. But time series really needs its own sort of dimension. Yeah, it's a very important concept. And if I find time, I will introduce you to that as well. All right. So having said that, now let me go and minimize this, and I'm going to introduce you to the idea of linear regression. Okay. Now, linear regression, if I just bring this, I know like you might be getting a bit bored because we're not coding yet, but I just want you to have a solid understanding of this before we go forward. So because we're covering linear regression, it's not too many slides. I just want you to be aware what we are going to be doing. So linear regression is the oldest and most famous method of, making predictions using some input data. And you cannot go in toward machine learning and all that, or deep learning, without having understood what linear regression is, okay? So let's quickly, I think most of you have an idea of it, but I need to sort of cover this, yeah? So imagine if we have a collection of labeled examples, xi, yi, basically, where n is the size of the collection, the number of samples. Let's say a data set with 10,000 rows or so, yeah? xi is the d-dimensional feature vector, meaning the how many data basically we are putting into the model, and yi is the real value target. Now we referred to features and targets previously, yeah. In other words, we have lots of x's in column 1 to 10, and we have one output, y. And we want to make a model that can predict basically the y for us, once it's trained on the x data and known y data. Yeah. Now, a linear model is a parametric model, basically. So what does that mean? It means that obviously there are some parameters that are involved in, like leading to the construction or like into the structure of this model. So if we say our model FWB or linear model is a function of W and B, which is a linear combination of features, and is parameterized by W and B. Now, I'm sure all of you have seen this before, okay? I am 100% sure that most of you, before even hearing of machine learning, you have seen this before. And we used to say y equals mx plus b, I think, for example, or ax plus b. That was the usual algebra. In machine learning, they like to refer to this, which we used to use A, I think, before. They used to like to refer to it as W, standing for weight, yeah? And B as the bias value. It has nothing to do with the other bias that are referred to, yeah? It's just bias, basically. Nothing related to the bias variance that I discussed earlier. They are really cool, linear regression models. They're super simple. They're rarely overfit. And the whole idea of us designing the model is to be able to estimate these W's and B's, the relationship between, to define the relationship between the output and the input, which is the X, in this context. And I mean, like I've put the optimization procedure here. I don't want you to sort of feel intimidated. Don't worry about it if this doesn't make sense to you at the moment. This is quite simple, actually. Yeah. So I can maybe go through the model and gradually digest this for you later. But this is really super simple. I mean, it seems really sophisticated, but it's not. Yeah. So let me do this. Yeah. Okay, so if I get rid of this for the moment. Okay, so what does all of that mathematics means? So imagine I have, why did that pop up? Let me just bring this to the center. So let's keep it simple. We are plotting two things against each other. So this is our X, yeah, and this is our Y, okay? So this is going to be, I'm going to just create some values basically for when you have X, this is going to be your Y, yeah? So this means when X is at this value, Y is going to be basically that value, all right? In simplest forms. Now let's say you come and make a model, all right? And this model, I'm just making it up, yeah? Is going to be, your machine learning model is going to be like this, yeah? That red line, okay? Now if you make your machine learning model, technically choosing this plane or this line or this hyperplane, these are terms that we will use later. This line basically resembles your linear regression model, your basic linear regression model. So in a sense, y, which is f of x, equals some weight multiplied by x plus some b, okay? And it's defined by this red line. Now, if you use the red line to predict y for the given x, so let's see, where does it go? So before, I mean, if you want to estimate it, you need to really go here, okay? So that becomes your y hat. That's the y you predicted. And this is your real y. How much error was there, guys? The amount of error is the difference between the real y and the y that you predicted using this line, okay? This is how you're evaluating your linear regression model. That's the best metric to tell you if your line is good or bad. Now, let's say some other person comes and says, okay, how about this line? You know, let's just make it, I think this thing fades actually. No, it's okay. So let's say somebody comes and says, yeah, well, I like this line. This seems more like it, yeah? And I'm going with this model. So if we want to make the same prediction with this model, so this is model 1, and this is model 2, okay? So if we want to make a prediction using this second model, well, we need to go and find y like this, isn't it? That becomes y hat. Now look at the difference, the error between the real y and the y that was predicted, y hat. So it's obvious that the red one is much better than that model, okay? So if you think about it here, what are we doing? This is y predicted, sorry, y real, and y hat is the predicted ones. So with this model, we make lots of predictions, and all we are doing, we are summing up, yeah, these errors that I discussed, yeah? So it just means summing up all these errors that our model basically creates when we try to make predictions. And that's the best metric in terms of trying to sort of evaluate our model, right? So that's how we optimize our model when we are basically training it, okay? Now, these are some of the metrics that we will be using: mean absolute error, mean squared error, root mean squared error, and R2 score, yeah? These are the parameters that we will use to test our model after we have trained it, to be able to say that, I got a really cool model, it's great, or it's a total rubbish, yeah? Unlike you, when you revise this video, if you're not familiar with these terms, come back to this part of the video, look at these and go and explore them further, all right? You really need to do that so that you have a good understanding of your evaluation metrics, because that's what we will be using. Now, having said all of this, let's stop with the boring stuff. Gradually, as we do more models and all this, these will sink in. If you still had some difficulties when you read about these and you don't understand them, then drop me an email, okay? And then I'm happy to cover it with you. But I'm sure you're all clever. Most of you probably know all of this. But if you don't, or if you have difficulty with it, let me know. Okay, so now I'm going to start. Let me just get rid of this as well. So, okay, that's it. So let's reconnect this, yeah? Now I've shared the data with you, which was called housing, US housing, yeah? It's just some data for that is used for machine learning training, yeah? And we are going to be using that. So we're going to start with our experiment, or first, week 8 linear regression, or first basically model. So let's import the necessary libraries, and I want you to do the same thing as well. I usually import NumPy as NP. What else do we know? Let's just import Seaborn as SNS, and let's just import Matplotlib for the moment as well. Import matplotlib.pyplot as plt. I think that's enough for the moment. I don't even know if you use many of them or not, but let's do that. Okay, so I have my libraries that I think I will be using, and I've imported pandas. Yeah. So one thing, this is on my drive. I don't know where you guys have this file. Obviously, I have it already installed on my drive, my Google Drive, so I'm going to take it like that. Otherwise, you guys know how you need to do it. Yeah, so you take it either if it's in your Google Drive, you just need to give the address. If you have imported it using this, here, then you just copy, right click, copy path, and you put the path basically there. So let's look at the DF. I've imported the DF. The first thing to do, yeah, is I'm going to say df dot head to see what is my data. Okay. So I got this table and it has some columns. All right. Whenever I get confused about these many columns, what do? I can say df dot column. Yeah. Sorry. Columns. That's right, isn't it? Wait. Column. Yeah. So 1, 2, 3, 4. Okay. So straight away I get the idea. This is about some data that you input the area of the house or something, the number of rooms, number of bedrooms, the population of wherever that house is, and the price of the house. And then you got an address as well. All right. Okay. So what sort of linear regression model are we going to be playing with this? I mean, what can be done with this? Well, how about this? What if we use these, yeah, and try to predict the price of the house? Okay, so shall we? So I'm going to say, let's make a linear regression model that can predict the price of a property once trained with certain input features. Okay, that's what we want to do, technically speaking. Okay, okay. Let's quickly look at some of the stuff we have learned before. So let's get a quick snapshot of let's no let's get a quick snapshot of our data statistics. Yeah. How do we do that? df dot describe. Okay, so area count 5,000 mean. The first quartile, semi-quartile. This is important if you want to sort of dive into the statistics of your data. Yeah, but I just used it so that it can be a refresher that you can, do these things and straight away get some statistics about how your data is operating. All right. Now, shall we do a quick pair plot, guys, using Seaborn? Yeah, because that's a fantastic indicator. It can show us if any of these columns are interrelated. Okay, so it's a fantastic. Yeah. Mm-hmm. Uh-huh. What you bring it to this environment? All right. Have you saved it in your Google Drive or have you downloaded it into your computer? Okay. Okay, you have it here, right there. Okay. Go there, right click on it, yeah, right click, and for example, my drive, call up notebooks, I don't know, data, let's say this, yeah, right click and you say copy path. You click copy path. When you do copy path, You come and put it here as a string. You paste it here as a string. All right, do you want to do that? Okay, well, don't put the same as mine because it's going to be different for you. This is the address to my directory. For you is to be copy path, basically whatever that path is, you put it here. And if you read it. Okay? Cool. Okay, let me just move on. So df.describe, where was I? Sorry. Yeah, I think I said per plot. Yeah. So let's go and try to sort of visualize this data. So I'm going to say, can I? I'm going to now basically say SNS. I've imported seaborn dot per plot, and I'm going to per plot what my data frame. Did I type that right? Yeah, hopefully. No, I didn't. Oh. Obviously, it's going to take some time when you do it. All right. Let me just minimize this for a second. Okay, so what do we see here, guys? We got average house age, average house number of the rooms, number of the bedrooms, and if you take it, I mean, like we don't see any correlation or linear relationship between these, do we, guys? I mean, we don't see any of them like a straight line, you know, like following each other, which is in a sense good. And also, we see some of this, you know, a number of bedrooms, for example, yeah, they come out like this, like these clusters, because obviously the number of bedrooms are discrete, so you don't have like 5.5 bedrooms or 5.6 bedrooms. It's like 3, 4, 5, 6, 7. Anyway, but what this is telling us, it's good. Because ideally, when you use machine learning models, it's good to use columns of data that are not correlated with each other. It usually yields better outcomes. Not specifically all the time, but that's one feature to follow. So far we know that none of these columns seem to be really correlated as such, except that somebody might argue that, oh, with average area income, I see some form of relationship with the house price. Well, arguably it may be because like it has this like tendency as if it's skewed, yeah, but it's not that elaborated. But yeah, you can see some patterns. Okay, cool. So let's go and explore this a bit further. Can we just see, guys? You might be like, hold on a minute, what sort of house price are we looking at? Yeah, I mean, what sort of figure are we looking at? Are these like all houses are above £1 million, below £1 million or so? Again, we use Seaborn, yeah. So if I go and say SNS dot this plot, okay, and df, and we want what? The price, isn't it? I think it was capital P, isn't it? Yeah. Price. Okay, so the property prices go anywhere basically from really cheap, probably like abandoned houses, maybe, I don't know, like, or houses that are possessed or whatever by the bank, and it goes all the way to maybe £2.5 million sort of house. Yeah, so that's the distribution of our data. It's moderately basically distributed across along, you know, like a margin of £1.5 million, for example. That's our like distribution of the price, basically, technically speaking. Now, one last thing, let's just look at the correlation of our data. Now, I'm going to introduce another feature of Seaborn, which last time I haven't shown you, and it's a heat map. It's a fantastic visualization method. Let's use a heat map to visualize correlation between the columns. Okay, so we're gonna say SNS dot heat map, yeah, and I'm going to say df. Okay, now it's important what I do here, guys. Yeah, so if I just show something there, df dot head, and I just want to look at the first element. Yeah, please pay attention, guys. In my data, yeah, I have columns which are numerical, all. Then suddenly I get to address. The address column is not numerical. Now there is no way that you can measure the correlation of the address in its current form, yeah, with the price or with any other column basically in there. Right? So it's impossible. So literally, and also the address in this form is not useful anyhow, right? So we need to do a correlation by getting rid of that, because it would even give us an error since it's not a numerical input. So the way I do that, again, refresher on pandas.iloc. So I'm going to select all the rows in my data, df.iloc, it means go to my data frame, .iloc, select all the rows, that's what that semicolon means, comma, and I want all the columns up to the last one. The last one is the address, so I'm not including the address, yeah? So if I do that, let me just, and I need to do the correlation of it, yeah, using the .core function. So .core, and I will get that. Now, this heat map takes every single one of my columns, okay, from average area income all the way to price, and puts them against each other. It's a correlation. I mean, let me just, maybe if I show it to you like that, it makes better sense, isn't it? You see, that is like the table where it shows the correlation between each of these against the other. Yeah, it shows us which ones are correlated. Highly correlated is 1, and then 0 correlation is basically dark here, right? So obviously everything is correlated with itself, price with price, area population with itself, so on and so forth. But you don't see significant correlation between other things except this one, which we also noticed it when we did this plot. Yeah, you see that's the highest correlation. You see average area income and price of the house. What does this indicate? That rich people or people with higher income tend to be sort of, buying higher prices, and people with lower income would be buying cheaper houses. So that is highlighted here, which is interesting. Okay. Anyway, now let's move on and start building our linear regression model. Okay. So cool. Okay. Let's get on with making our first model. Now, to make our first model, obviously we need to have our data, right? We need to have our data. Now, I showed you how to select the columns using iloc, okay? That's one way of selecting your columns. Perhaps I can go and now show you a different way of doing it, yeah? And that is, if I say, let me just write this, df dot column, okay? So if I say x, my x's, yeah? X equals df and double brackets. I'm using this so that, it's a refresher for your, pandas as well. I'm going to copy paste that. So that's my x, all right? And you see I've got rid of address from there. And I haven't put price, guys. Yeah, please pay attention. I didn't select the price because price is going to be your y, isn't it? that we want to predict. And I'm going to say y equals df, again using pandas rules, and I'm selecting price. Let's see if I've done this right. Okay, let's double check, make sure nothing is wrong. Okay, as if everything is making sense. So that's my x's. Okay, so x is my data in terms of these columns. All right, these are the input features, the x's that we are going to be basically feeding into our model. And area population, and what is my y? The price, what we want to train the model and what we want to predict ultimately. All right, fine. So how much of this data are we going to use? I mean, how much of this data are we going to use to train our model? Well, somebody, I mean, like, let me just answer it as well. All of it. Well, if we use all of it, sorry, if we use all of it, then how can we test our model performance? Huh? It's like as if you take your child into a school or something, they teach him loads of stuff, they give him loads of notes, and they have given him everything, and even they have given him the exam questions. So how are you going to test that kid? Nothing. You just say, all right, I trained him, but hopefully he has learned. And that's not the approach that we take, in machine learning. So how about with maybe 50% of the data? In which case, then we test it on remaining 50% that we keep it hidden from the model. Okay, would that be a good idea? Some people can argue it depends on your case. Yeah, maybe you want to have a model that is performing amazingly well, so you want to sort of really put it, on a hardcore test. Yeah, like you will be testing it significantly. But usually you get people to train with about 80 to 70% of the data and then test it with the remaining 20%. Okay, so that's what we will be doing. Yeah, and this is most conventional. Okay, and we are going to just stick to that. So fine, we need to split the data. Good God, how are we going to split it? Shall we just go and cut half of it, But then that's not right because we might be biased and feel, like, okay, like just going and chuck, selecting the first half of the data or first 80% of the data. Well, we use scikit-learn, yeah? Scikit-learn has a class, train test split, that enables us to randomly select certain percentage of these data for training and testing. So let's use scikit-learn library, okay? How do we do that? To do it, first we need to import it. First, import the library, okay? And, well, not the library, but the module from the library, that's what I mean, okay? So I'm going to say from sklearn dot model selection import train test split as TTS. Okay, train test split as TTS. Right. So I'm going to run that. Okay. Now what I'm going to say Okay, remember, what data do I have, guys? I have an X and I have Y's. Okay, I have X and Y's. I want scikit-learn to go and pick 80% of this data randomly, along with 80% of my Y data, and keep it separate from 20% of this and the 20% of the Y associated with it, hidden. Okay, that's what I want scikit-learn to do. Fetch out 80% of these data so that I can train my model with. That's what I wanted to do. So now that I have imported train test split as TTS, yeah, I mean, you can import it as Mickey Mouse if you like, but TTS is it's a shorter term, isn't it? Some people even just import train test split and use that. Now, I'm going to say this syntax is important, guys. X train, X underline, train, X test, then Y train. The order needs to be exactly this, yeah? And Y test equals TTS, which we just imported it as TTS. And I'm going to give my X, I'm going to give my Y, okay? I'm giving my X to it, yeah, X. I'm giving my Y, and now I'm going to define, we said what? 20%, yeah? So test size, 80% of the data for training, yeah? Train 80%, so that means 20% testing, yeah? So then I'm going to say test size equals 0.2, yeah, isn't it? So that gives us, and then I'm going to define another thing here. You don't have to do this, but if you want to have similar results to me, you just say random state equals 42. This just means that randomly you and me, we all are going to have the same sort of a splitting done, yeah, because we are setting the seed to 42. As I said, you don't have to do this, but then it means when it goes and fetches the data randomly, your data would be different from me, unless you set it at random state equals 42. So let's do that. And now I have my X test and X. Let's look at some stuff here. X train dot shape and X test dot shape. Okay, cool. So we had 5,000 data. Do you remember? He has kept 1,000 of it as our X test and 4,000 of it as our training data. How about our Y's guide? Always, I think, do this, especially when you're a beginner. Again, train, Y train, and Y test. Let's just see if everything matches. Oh, we see it. Shape and dot shape. Yep, perfect. These two needs to match your tests basically, and these two needs to match together, which is all fine. Okay, so that's your Y test, Y train, and that's your Y test. That's X train, and that's X test basically. All right. Now let's get on and make our first model. Okay. So again, to construct our model, to construct our linear model, we will use scikit-learn again. Okay. So again, this means we need to import something else from the scikit-learn. And what do we import from it? Well, the name is on it. So from sklearn dot, okay, linear model. Okay, so before we used model selection, here we call it, it's on the linear model subcategory. From sklearn, linear model, we want to import the linear regression class, basically. Yeah, and if I do that, cool. So here I just imported the LR class, yeah? Very important, guys. From this point onward, you need to pay attention. So I imported it at the moment, yeah? I imported the class. Now I need to make an instance of this class, and we're going to call it, I don't know, model LM. Let's call it LM, linear model. LM equals linear regression, okay? And I'm going to leave it simple, just like that. LM equals linear regression. So what do I call this? We usually refer to this as I just made an instance of the LR class, yeah? LR class, I mean the linear regression. I just made an instance of it. Okay, so I've brought the model in. Is it trained yet? No, I've just got it ready. It's ready to go. So now that I have my model ready, let's train it. Okay. So how do we train it? Quite simple. We're going to say lm dot fit. We use the dot fit method. Yeah. So what do we train it on? lm dot fit with our training data. And let me just put this here. We train the model with our training set of x and y, and we use the dot fit method to do so. Okay, that's what we do. So lm, I made an instance of it here of the linear lm dot fit what with the training data. X train first goes into your x's. Second is the y train, right? And third, well, nothing. That's all you need. Your x and y training set. So I'm going to run it and I'm going to get an error. Why? Because I haven't run this. Okay. Although I wrote it, I didn't run it. Always, sometime when you get an error like this, pay attention. You see they have a green tick mark. I don't have that. So now if I run this, that's it. My model has gone through those training data and it's fitted. Okay. So shall we now go and evaluate the model? So first, just see. I hope that you're all aware of these terms that we use. So if I just delete all of that. Oh, come on. This is quite annoying, actually. Why do I need to, like, delete these one by one? Oh, that was a hard job. I'm sure, like, it's easier way to do it. I'm being clumsy. Anyway. All right, so if we want to think of a linear regression model in its, I use the old, like y equals ax plus b or something, as you're familiar in old terms. In reality, it's going to be, in say machine learning, it's going to be wx because we refer to the a as weights and plus b. Okay. Now this is the intercept, yeah. And these are the weights. Okay, the weight, not the weight, sorry. So technically speaking, this is what we just did. Okay, so what I just did here, linear regression, we fitted the data and we created our line. It's like as if we gave part of our data to it, the training data, the X train here, and the Y train here, and we basically ask the model to go and fit. It defined some relationship, did the calculation for us, and let's say it has created this line. Okay, so that's what it has done. Now we can find the intercept of this, the B, okay, and we can know what W is for this particular model, right? So now I'm going to see what is the B, what is W, okay? And how do I do that? I'll go and say LM, which is our model, dot intercept, yeah? Intercept, yeah. It's telling me that the intercept is 26,000, oh God, 263,500, or is that million? Yeah, 2,635,000. Well, negative. That's the intercept. That's what this model has found. How about the coefficients, guys? LM dot coef. Yep, that's it. All right. Now, can I have your attention on something? Because obviously I oversimplified the visualization. Now here, I wrote this, but this is really when, this only applies when I had, if, let me just, this applies only if I had, let me just see, how can I get this thing away? If I had a data as such, let me, okay. So, if my data was like this, yeah, if it was, for example, number of bedrooms, and then house price, then I would be dealing with a model like this, yeah, because it's just one parameter, y equals wx plus some b, okay? If that was the case, if it was just one parameter. But you know we had many columns, right? We had multiple columns. So really it's the real model that we just trained is like this. Y equals W1 x1 plus W2 x2 plus W3 x3. And how many columns do I have? 5, wasn't it? Yeah. So 1, 2, 3, 4, 5. Yeah. So technically, this is the model that we are dealing with, plus W4 x4 plus W5 x5, and then plus that intercept, yeah, B or intercept. So really, guys, the model that we just trained, that's the mathematical relationship that we just fitted, okay? Now, can I visualize this, guys? No, there is no way you can visualize this because it's in multi-dimensions, okay? So from this point onward, you are entering into the world of multi-dimensionality, and obviously you cannot, visualize this. It's not as simple as saying, yeah, that's my x's, that's my y, let's just plot it, this is the line. It doesn't work like that, because even if it was like x1 and then x2, then we could have a hyperplane, like a surface. But once you have x2, x3, x4, sorry, x3, x4, x5, that's it. You cannot visualize it, yeah? So our model is technically, drawing a hyperplane in a multi-dimensional space that human vision cannot basically comprehend it. So you just accept it mathematically. So these values that you see that I just said, lm.coefs, these are the weights, W1, W2, W3, W4, and W5. That's what we just calculated, okay? So now that we have done this, literally we have created a mathematical relationship. We can come and say, I mean, not we haven't evaluated our model yet, yeah? But we can come and say that, okay, this is the model that we created. Like, if you want to estimate the price of a house, you need to multiply this W1 by its average area income. You multiply this W2, which is this value, by its area plus average house age or something. And then when you sum them up, it should give you an estimation of this basically thing. Yeah. So that's what it basically is trying to tell you. But hold on. Let's actually see how good is our model. And how do we do that? Remember, we kept 20% of our data hidden. I shouldn't have done that. Okay. So we kept 20% of the data hidden. Let's see if the model can predict those prices correctly. Okay, that's what we're going to do. Let's see. So, how do we do that? Our LM model is at the moment trained. Okay, so now we're going to basically test it on our X test data. Remember, on our X test data. Okay, so or Y predictions, I'm going to call them Y preds. Yeah, so Y pred, or can we call them predictions? So you don't. No, let's just call it Y pred actually. Y pred equals, yeah, Y pred equals LM dot LM, which has been fitted already. Yeah, so we have designed our hyperplane basically in multidimensional. So LM dot predict. Okay, LM dot predict. Predict what? The X test. Okay. Remember, we trained with X train. We are now making predictions with X test. Let's do that. And we have now our Y predictions. Okay. Well, how good are they? I mean, like, do you think it's going to be like, has he predicted it right? Well, let's take a look. I'm going to say, I'm going to use matplotlib plt.scatter, because if he has predicted it right, if we plot the predictions with the real stuff, yeah, so let me just write it here, actually. Let's plot the price prediction, which is Y pred, by your model, against the real Y values, which were Y test. Okay, so that's what we want to do. Okay, and if we scatter them, if we scatter plot them against each other, we should get something like, you know, as if they're correlated or they're like moving in the same direction. So I'm going to say plt.scatter Y test in the x-axis and Y pred. Yeah, let's see. Well, hasn't done bad. Okay, it's cool. This is basic visualization. Would you say that this is really good or this is really bad? Well, we need to check this out actually. Yeah, we need to check this out. But so far so good. Yeah, that's what it seems. And if I say, if I go and now try to see how much error we made. Do you remember, guys, that I said that, you know, our model would be predicting something and the real value would be something else? Yeah, we need to now evaluate that, and that's where those evaluation metrics, you know, like come in. So to my evaluation metrics, like I told you, there was a slide that you need to go and look into these and properly make sure you understand them. Yeah. So mean absolute error, mean squared error, yeah, and root mean squared and R2 score. Okay, these are the important ones. So I'm going to say let's use sklearn metrics to see how our model performed. Okay, let's see that. And to do this, we're going to import something else again from scikit-learn, from sklearn import metrics. We can say that. So I'm importing metrics. Learn scale LEARN, sorry. So I'm importing the metrics, yeah, and I'm going to now try to basically find out what's the MAE, yeah. So for MAE, I'm going to say, for example, print MAE, all right? The MAE is going to be, and I'm just going to put, I'm going to call the metrics, which I've called from scikit-learn, dot mean absolute error, yeah? Where is mean absolute error? Mean absolute error. Okay, mean absolute error of what? Mean absolute error of y test and y pred. Let's see what value do we get. 8087. Okay. We can also go and do this and get the mean squared error just the same way, and that would be print MSE, mean squared error of the model. Oops, I shouldn't do that. Mean squared error, and I'm going to put here metrics dot mean squared error. Yeah. Mean squared error of what? Again, y test and y pred, right? Let's see what do we get here. And we get that value, all right? And I got a homework for you tonight, yeah? So I'm getting these values, and finally print R2. Sorry. R2, and I'm going to say metrics dot R2 score. R2 score of, again, y test and y pred. Okay, 91.79. yeah, I can give you some hint. This is pretty good, in fact. Yeah, it means the model has been, you can think of it as about 91%, think of it, yeah, interpret it like that. It has been 91% successful. It doesn't exactly mean this, yeah, it doesn't exactly mean this at the moment, but I want you to think of it like this, that it's almost pretty good, yeah, in terms of predicting the house price, yeah. But in reality, the R2 score has a different meaning in terms of, concept. And that's what I want you guys to do, because, at the beginning of the lecture also I told you that can you please go and pause that section, read about them. And once you read about it and you know what they are, then come and consider in these data, what was the average house price, yeah? What sort of price ranges were they? And what were the errors? Yeah, what were the errors in these predictions versus, real prices. And then try to make sense of these values. Yeah, this is your homework. And then consider, is R2 score a better factor to consider in terms of how good your model performed? Or is MSE or MAE? It's really important. This is nothing that I can teach you in a sense. I really want you to dive into these parameters. Why? Because for the next coming weeks, if you don't have a solid understanding of what these things mean, there is absolutely no point. And that's why I'm emphasizing that you dedicate yourself this week, if you don't know, to fully understand what these regression metrics are all about. What do they mean? And finally, no, I think that's about it. That would be good enough for the moment. So, yeah. So this was a light touch, guys, on linear regression, or most basic form of machine learning model. And I wanted you to sort of get a feel for it. So hopefully next week when we start, we would be spending much less time on introducing, the idea of machine, because we sort of got introduced to what machine learning is. So rather from next week onward, I will explore every single model separately and we focus on that model. But that's really important. Please, I'm telling you that you practice with this. This is the simplest form. You need to have understood what this train test split is all about. You need to have understood how we evaluate these models' performance. If you don't understand these basic concepts, yeah, the train test split, the evaluation metrics, okay, and why prediction versus why real, why test real. If you don't understand these concepts from next week onward, you would struggle. Yeah, and things start to make no sense basically. So while it's light, while it's, like we are just at the beginning, watch this lecture. Make sure you completely understood what we covered today. All right. Apart from that, I'm going to say now bye to you unless you have a very, very important question from me. If it's not very, very important, then you can just say bye, Ali, and we can say goodbye and see you next week. Okay, well, thank you very much, guys. I love you guys. Go and enjoy this. I hope you go and practice with this, and I see you next week. So gradually, we will become, lectures become more exciting and more machine learning like. Okay, and I hope you have enjoyed it. Okay, well, thank you very much. Take care, guys. I'm going to cut the recording now. No problem, guys. Take care. Have a good night. Take care.